buffers. Evolution has figured out some nifty things, and one of them is just how to keep you alive with carbon dioxide in the atmosphere. Okay, so these buffers are just literally all over the place, and it's kind of neat. I mean, the reason why they're all over the place is because there's only how many strong acids? 6. Everything else in the world is a what acid? Weak acid. Therefore, it's a buffer. All weak acids are buffers, and that's what we're going to hit on a lot today. So a lot of this stuff, like these weird acids that you maybe never have heard of before, they're all buffers, okay? Because they're not members of the 6. Okay. Now the purpose of a buffer, Sochi, is resist changes in, what'd you say? I can't hear her back there. Say it louder. pH. Yep. All buffers are mixtures of, Christina, a blank and a blank. They have to resist changes in pH, so they have to be a mixture of a what and a what? Conjugate acid and a, well, she's using the right words. I was just thinking acid and a base, right? But conjugate acid and conjugate base sounds even better, right? Conjugate acid. Because we're dealing with those weak acids, we didn't really use the word acid and base. We kind of used the word conjugate acid and conjugate base, right? So how do they do their job? Monica, how do they do their job? You're going to slam a whole bunch of Coca-Cola or something. It's kind of acidic. Something's got to be helping your blood out there.
They're going to react with, like it's really acidic, the base is going to react with acid.
Yeah, if it's really acidic, right, this one will react. Exactly. No, there it is. This one will react, right? If you consume, metabolize a bunch of base, then this one reacts, right? So, and then there's a limit to it. The conjugate acid is going to disappear after a while. There's only so much of the stuff. And the conjugate acid gets converted to conjugate base. So it is consuming, it is getting a little bit more basic, but it's a weak base. So it's not, the pH isn't changing drastically. You can't keep it absolutely no change at all, but you can really slow it down and reduce the effect. Okay. So what pretty much whenever you don't have to use Henderson-Hasselbalch, but whenever you see the word buffer in any question, we'll jump to our Henderson-Hasselbalch equation, because life is going to be so much easier. It's prepped and it's organized for all these pH problems. But let's see how they get it. If I take the log of both sides, so here's our weak acid, our Ka expression, right? This would be our Ka reaction, right? HA equals H plus A minus. Ka would be the products over reactants. If I take the log of both sides, I'd have the log of Ka is the log, what is this? H plus times A minus all over HA. Whoop. How can I, do you remember playing around, since Jose has the day off? Destiny, do you remember what's the rule with logs? Like, and you have this multiplication thing in here, or division, and you take the log of this product of all these numbers. How did that work with logs? Do you remember? Because logs could break it up.
Didn't you just separate each one? So it's like log of H times log of A.
Yeah, is it log of H times log of A? Or is it log of H plus? It was plus. So that's what we want to do to help ourselves out and give ourselves a... Because the log of H plus is really close to what term? pH. We're getting really close. Because buffers, that's really all you're concerned about. Oh, what is the pH going to be if this happens? Well, let's set up an equation so it'll look like that. So if we bring the log of H plus to the other side, it actually have a negative sign in front of it, right? Because you have to add it negative both sides. Bring the log of Ka, negative log Ka to both sides, so you have a negative sign in front of it. But negative log of H plus is, everybody? pH. So pH equals negative log of Ka would be pKa. And that's because that's the P function. The P function is just negative log. So pKa plus the log A minus conjugate base over the conjugate acid. Okay? But I say this technically is the Henderson-Hasselbalch equation. But I say let's use this one. It's easier. What did I do? Or what did I realize? Because nothing really, pH, pK, they're the same. But I changed my concentration to what? Moles. Why can I do that? Liters will divide. It's the same solution, right? So you have one buffer solution. You have the same volume. So liters divide out. One less complicating factor. It's not a whole lot easier, but it's easier. And actually, in the homework, it will be a lot easier. You don't have to worry about a lot of things. So I think that's the one we should use for Henderson-Hasselbalch equation for all buffer problems. The moles of the conjugate base divided by the moles of the conjugate acid. Take the log of it. Add the pKa. Where do you get these Kas, Mariella? Where do you get all these Ka numbers? Yeah, table or Google it, right, if you don't know what it is, because there's gazillions of weak acids in the world. Okay. However, when the volume of a buffer changes, just add some water to it, right? That could happen. You could make a buffer and add a bunch of water to it. The ionic strength changes. The chemical environment changes. Therefore, the pH changes. Whoa. Not according to this. Volume canceled out, right? The pH can't change if you add water. Yeah, it can. Because we're not supposed to use concentrations. We're supposed to use activities, right? But I think you'll be happy to know that, well, maybe you will be. Like in general chemistry, remember when we introduced significant figures? Ooh, we were so worried about it for 3 days. And after that, we just said, carry 3, 4 digits. It's the same with activities. It's not that hard. I don't know why they don't stick with it, but they don't. So I'm following the book. The book says it. Yeah, you should use activities, but do they? No. So that's okay. We'll do what the book does. Okay, but just realize if life or death depended on it, I would use activities. Appendix G, now I bet no one brought their book, so I spent some time. Oh, you did? Oh, if you brought it, it's going to be so much better because you're going to be able to see the compounds better. But you don't need it yet. You don't need it yet. Wow, so many people brought their book. I should give an award. For bringing their book. So that appendix has a lot of weak acids and the corresponding pKa values. But how do you pick the best buffer for your application? So let's see if I can pop one open here. I'll just go down here. Oh, it didn't save it. Son of a buck. I didn't swear, though. I'll have to go find it. All this stuff. Okay. So here's an example of... Why does it go do that? Okay, here's an example of... oh, you can't really see. This column right here... can I write up? No. This column right here is the pKa column. Okay. Here's your name. Here's your structure. And then here's all the pKa's. So... I don't know, your pH is really strong for the synthesis of some compound X, and it's really expensive because this one ingredient, this one compound is really expensive, and your starting materials are expensive. You want to make sure that pH is right so you get the maximum theoretical yield, for example. Okay, so and the reaction has to happen at a pH of 2.2. So these buffers, that's their job. You put them in solution. Hopefully they won't interfere with what you're doing, but they should keep the pH at 2.2, as close as possible, right? So how do you pick it? All you do is pick the buffer whose pKa is closest to, what number did I say? 2.2. So, yeah, I thought I saw something close to 2.2. There it is. Yeah, I did see something way up there. Glutamine. Glutamine. You'd use the glutamine buffer. Okay. So that's how you pick. That's how you pick a buffer.
Is that why they put a lot of things in like PK and PKB like online and in books and stuff?
Well, yeah, maybe not so much for picking a buffer, because pretty much all the procedures that we end up really doing, they tell you the buffer to use. But if you're doing a research project, then you'd have to be looking up the pKa. But I think they list them all because of that Henderson-Hasselbalch equation. Whenever you want to find the pH of any buffer system, you have to plug in the Ka of it. So I think that's why they list them all everywhere, for that Henderson-Hasselbalch equation. Okay. So, but once you do pick a buffer, and you should know this because it's in the homework, they say, how would you actually prepare this buffer? And it's not really that bad. I mean, if you wanted, I don't know, 25 milliliters of 0.1 molar glutamine, okay, just figure out the number of grams that you're going to need. So multiply the volume in liters times the concentration. You get moles. Then what the heck is glutamine? Google it, find it in the table, right? And then get the grams of the stuff. So you mass it out, and you put it in some, probably a 25 ml flask, since that's what you want. And then you're going to dissolve it, get it to dissolve. But don't fill it up to the mark yet because of this step here. You dilute it, get it to dissolve, and maybe 20 mils or so, right? Because you know as you dilute, it changes the pH. So get it kind of close to the final volume, and then adjust the pH by adding small amounts of strong acid and strong base. Literally, you just kind of dip your disposable pipette or something into NaOH solution and kind of dip it into the buffer and squeeze it in and out. And if you go too far with pH, then go with the acid. Go too far, and that's all you're doing. You're sitting there playing around with a little pH meter in there until it gets to be 2.2 or whatever you're shooting for. And you go down below. You can't screw it up. Because if you go too far, I go to 2.1, oh, I got to add some base. 2.4, added too much, right? All you're doing is messing with the population of conjugate acid to conjugate base. You can't screw it up. So you just keep doing that until you get the pH you want, and then you dilute it up to the mark with the water. Okay? But the reason why for using this, small amounts of strong acid and strong base is, right? You only have 25 mils to work with. You don't want to add too much. Okay? All weak acids, or buffer systems, are named according to their... Anybody know? It's not acidic. It's their neutral form. Okay, so we need to practice this. We really don't need this so much for today as we are going to be for next class period. But you want to be able to figure out what the heck is going on here. So determine whether the name of each buffer corresponds to the acid or the base form. So, and you're going to see in that table, the neutral form could be the conjugate base form. The neutral form could be the conjugate acid form. It just depends on which form is neutral. So let's take a look at one of these. Formic acid. Now, if you've got your book, you could probably, I don't know, can you see this? Well, you can kind of see this. The other one didn't work so well. But you see formic acid. It's in that appendix AP11. And there it is up on the very top. Now, this is their convention. The blue H is what's so special about the blue H? That's the acidic hydrogen. So if you see two blue H's, well, then there's two acidic hydrogens, and you should expect to see two pKa's. Okay? Now, formic acid is way at the top. That acidic hydrogen is in blue. It's kind of nice because you could get the molar mass of it and all that kind of stuff there. But the neutral form is what's in the bottle. The neutral form is what's on the shelf. So that's why they always name it by the neutral form. Does that neutral form correspond to HA, the conjugate acid, or A minus, the conjugate base? HA, because that hydrogen's attached. So formic acid definitely corresponds to HA. Where'd that go? HA. Guanidine. Where's guanidine? I think that was on the bottom. Here's guanidine. Okay, here's guanidine. Does guanidine, well, how many acidic hydrogens does guanidine have? Oh, I see what you're saying. There's a little subscript 2 on it, but there's only one pKa listed. So it only has one acidic hydrogen. Okay, it only has one acidic hydrogen. But, that's just an extra question. But does guanidine, the name guanidine, refer to a conjugate acid or a conjugate base? The conjugate base form. Because, see this? You see the little plus? So that means, and all of these forms are always HA. The table always has HA because you see all the blue H's. So these are always HA. But you see a plus sign there. I got to get rid of that acidic hydrogen to make it neutral. So guanidine is actually a neutral compound, but it corresponds to the conjugate base. So that's a A minus for guanidine. Okay. Ethylamine. Does that make sense, Daisy? Ethylamine. Okay, find ethylamine and on the bottom, and write down whether it corresponds to the conjugate acid or conjugate base form. Corresponds to the base. Good, the base. I think there's one more. Bipyridine. Oh, we said base. It's supposed to be A minus. The base, bipyridine. I think I gotta look in here. Here. Corresponds to the, everybody agree again? Conjugate base? Brad, you agree? Good. Okay, so it's just something that we need to remember mainly for next class period. Okay. So here's some questions. Solution contains 63 different conjugate acid-base pairs, 63 different weak acids. Among them is acrylic acid and the acrylate ion with the equilibrium ratio acrylate over acrylic acid 0.75. What is the pH of the solution? What are they trying to get across with this question? $63. Seems to me there's 63 Henderson-Hasselbalch equations you could write, right? But will they all have the same pH? Yeah, it's one solution. It's one solution. So it's odd, but it's like we got so involved in the math, I think we might have missed the beauty of it. It's those big, long, it's odd to say math is beautiful, but it's really interesting because you did this big systematic treatment of equilibrium. You wrote gazillions of equations. Every single one of them is simultaneously valid at the same time. H plus is H plus everywhere. It doesn't matter where you start, how it works. So it doesn't matter which of these 63 equations you use. They're all equally valid. You can get the pH from any of them, right? So that's kind of what they're driving at here, is that yes, they are all interconnected, and they all reflect one another, and they all interfere with one another. But they just told you this is the ratio, 0.75. So there is some pH in that system, and it's influenced by all these 63 weak acids. It influenced them to create that acrylate to acrylic acid ratio to be 0.75. So you pretty much just write whose equation? Henderson-Hasselbalch. And just with this one system, you can get the pH. Right? pH is pKa plus the log. We said the moles of the conjugate base over the conjugate acid. But that's the same as the concentration of the conjugate base or the conjugate acid. So we pretty much just plug it in. Our pH would be 4.25 plus the log of 0.75. And sometimes you got to watch these guys, right? Because they try to trick you, and they'll flip this. They'll put the conjugate acid on top and hope you don't recognize it, right? I hate those tricky questions. But that's pretty much all you got to do. Describe how to prepare 100 mils of 0.2 molar acetate buffer, starting with pure liquid acetic acid in solutions containing 3 molar HCl and 3 molar NaOH. The only thing you're really missing, well, you're really not missing it because I'll be giving you all these tables of weak acids. So if you don't know what acetic acid is, I guess you could just look it up in the table. But does anybody know what it is? H. An acetate with an extra H. So what's the acetate? C2H3O2. With a negative, then you attach on an extra H. Right, there's your acetic acid. Okay, so let's see if you can describe the steps. Remember the first part? What was the first thing you had to do? Get the... Yeah. Well, it's not really a solid, it's a liquid, but it doesn't matter, right? Mass is mass. See what to do, Daisy? So we've got, this is moles per liter. You multiply it by this, you'd have moles. And then figure out what the molar mass of this thing is. Then you get grams. And that's the first step. And then you dump it in like this size flask, add some water, adjust the pH. Yep. I think it'd be easier because you have that bottle of that liquid and just take maybe one of those little automatic pipettes or something and just slowly drip it out onto the balance. Okay. It'd be easier to mess with than a solid, I think.
Oh, no, I would just do it in terms, usually I treat liquids in terms of volume.
Yeah, it is kind of, it does sound odd as to be massing out a liquid, but it works. Then you need to know the density then. But I would just, those micro pipettes are so easy to get nice little drops. That's why I think of micro pipette, because you just suck some up and then slowly squeeze out the little drops and mass out what you need.
Yeah, I guess we don't need density in this case.
No, you could though. Yeah. What is the molar mass of acetic acid? Daisy, what's the molar mass of acetic acid? 60.05. Thank you. About 1.201 grams. Okay. So add about 1.201 grams to a 100 ml vol flask. Add maybe, Albert, how much water? What would you do? Add maybe, you don't want to do 100 because, you know, in later steps you have to adjust the pH. It really doesn't matter, right? Just somewhat close to the mark, like maybe, because you're just dumping it in. So dump it up, I don't know, 50 mils, 70 mils, something like that, so just to leave some space to add acid and base to, right? So fill up 3/4 of the way or fill up 4/5 of the way. Fill flask mostly full or something. Adjust pH to, oh, I guess you could say with. Right? And pick your strong acid or base. The concentration doesn't matter either. A little more concentrated might be better, though, because then it depends on how, bless you, how concentrated the buffer is. It's not very concentrated. So just a pH with some acid and base, strong acid and base, you don't, and then fill the mark. Okay, with water.
So, on like an exam question, would you want us to like put it in list out the steps?
If it asks you to describe how to prepare, yeah. If it says describe how to prepare, make sure you describe how to prepare. Given the pKb for nitrite, 10.85. Find the quotient in a solution of sodium nitrite. So none of this stuff might look familiar, but this ratio, where have you seen the ratio? In the, what's the name of the guy's equation? Henderson-Hasselbalch. So when you see stuff like this, that's the clue. Use the Henderson-Hasselbalch. It's the easiest way to get the answer. So we'll get that. Now the quotient is kind of flipped, so we'll have to flip it. That's okay. We can flip it. So, but we can get that quotient from the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation, though, doesn't have pKa. Sorry, it doesn't have pKb. It has pKa. How's that going to work? If you know pKb, what's pKa have to be? Here's a hint. What's Ka times Kb? Kw. All right? So, and Kw is 1 times 10 to the negative 14. Okay. So, pKa, so pKa times pKb is 1 times 10 to the negative 14. What's pKa plus pKb? I don't know if you can do all that. It's just going to be, because pH, like 1 times 10 to the negative 7 is a pH of 7. So pKa plus pKb must be maybe 14. Just 14, right? If you're not comfortable with it, you might want to work it out. But pKa plus pKb, 14. So if you know what pKb is, you can easily find pKa. Substitute in the Henderson-Hasselbalch. They even told you what pH is. Solve for that ratio. But that ratio is inside a log, so you got to remember how to get rid of the log, and then flip your answer. See if you can get it. And we'll work it out. So there's several steps in here. Yeah, I would. Yeah. Except they want concentration, so you might want to say concentration of A minus or concentration of HA. But this is what we're going to solve for. you have to solve for that ratio. Flip it when you're done. We had 2 high scores. They tied. Congratulations, Alyssa. And for I think the first time ever, our OLLU Chemistry Club Honor Society President Mateo. 14 minus 10.85. It's 3.15. So you have to raise both sides to the what power? 10, good. 0.0707 or so. But then you gotta flip it. Oh, 14.12. That's about what I got. You get that? 14.12? Maybe? G14? For shame. No, to get rid of this, I raise both sides to the 10 power. Because then that will cancel out that log, 'cause they're inverse functions. So raise this to the 10 power, and raise this to the 10 power, and those two are kind of inverse. Like x times 1 over x kind of thing. Does it make sense? I don't know, that's what I got. And no one else has verified it yet. Okay. So somewhere around there, depending on your rounding. How did I get the 0.07? This one? So I had to flip both sides. So I'll flip this side, you have to flip this side. So 1 over 0.07079 is about 14. So your exams are up here. Have a good weekend.